Good morning, ma'am. I am Sajay from Triply Department. Today, AAT topic is about automatic power factor controller working and benefits. What is power factor? Fundamentals of electrical efficiency. Definition of power factor. Power factor is the ratio of real power to apparent power. Is an AC electrical system indicating how efficiently electrical power has been used. Types of powers. Real power performs actual work while reactive power supports the voltage for active power flow. Apparent power is a combination of both. Ideal and practical values. An ideal power factor is 0.1, 1.0 or unity. Achievability only when the load is purely resistive. Practical system usually operates at lower power factor due to inductive load. Consequence of power factor. Low power factors leads to inefficient power usage, increased losses, higher bills, large capacity equipment. Why power factor matters in electrical systems. Impact on performance, cost and grid stability. Electrical system efficiency. A high power factor ensures minimal losses in transmissions and distribution, improving overall system efficiency. Reduced energy cost. Utilizers often charges penalties for low power factor. Correcting it reduces operational cost and avoids surcharges. Equipment longevity. Poor power factor causes overloading and overheating in equipments, leading to frequent failures and reduced lifespan. Grid stability and load management. A stable power factor minimizes voltage drops and improves load balancing, enhancing power quality and system reliability. Types of power factor corrections. Manual versus automatic controllers. Manual power factor corrections involves manually switching capacitor banks based on observed power factor readings, effective but labor initiative and prone to delay. Automatic power factor correction APFC uses microcontroller based on system to continuously monitor and adjust the power factor in real time by switching capacitor banks as needed. Suitability and applications. Manual systems are used in small setups with stable load, while APFC is ideal for dynamic loads in industrial commercial environment. Comparative efficiency. APFC offers higher accuracy, faster response and better optimization of power factor, leading to lower energy losses and operational costs. These are the types of power factor correction. What is an automatic power factor control APFC? Smart automation for efficiency energy uses. Definition of APFC. An APFC is a device or system that automatically maintains optimal power factor in electrical system by switching capacitors as needed. Real-time monitoring APFC. Automatic power factor controlling system. You continuously monitor voltage, current and phase angle to assess power factor and triggering corrective action. Capacitor banks management. It dynamically switches on or off different capacitors in the bank depending on reactive power demand. Digital control system. Modern APFC's panel integrates microcontrollers, sensors, and communication interfaces for intelligence decision making. Working principle of APFC. Real-time detection and reactive power compensation. Sensing electrical parameter. The APFC sends voltage, current and phase difference to compute power factor dynamically. Microcontroller logic. A programmed microcontroller process input data to decide the required reactive power compensation. Capacitor switching mechanism. Electromechanical relays or thyristor switches activate capacitor banks as per computed compensation needed. Feedback and regulation. The system continuously monitors outcomes and adjusts operation to maintain optimal power factor. Key components of an APFC panel. Architecture of an intelligent correction system. Power factor controller, current and voltage sensor, capacitor banks, Switching devices. Power factor controller, microcontroller based unit that calculates and manages the switching of capacitors. Current and voltage sensor monitor the real-time parameters required to compute the power factor. Capacitor banks composed of several capacitors connected in a bank to provide reactive power. Switching device, electromechanical contacts or thyristor switches controls the connecting of capacitor banks. Step by step operation of APFC, reactive power correction in action, parameters activation, power factor calculation, decision of logic executions, capacitors activation, parameters activation. Sensor detects voltage, current and phase angle continuously from the load. Power factor calculation. The controller computes the real time power factor using the accurate data. Decision logic execution. Based on target power factor, it determines the necessary compensation level. Capacitor activation. Corresponding capacitors are switched on via relays or thyristor to supply reactive power. Role of microcontrollers and sensing units. Brains and eyes of the APFC system. Sensor functionality. Current and voltage sensor feed critically parameters into APFC system for analysis. Microcontroller algorithm, embedded logic processor, real-time data and determine necessary capacitor activation. Dynamic load response, high frequency monitoring allows fast adaptation to fluctuating loads. Data communication interface, modern APFC units support Modbus, RS-485 and IoTs for remote monitoring and diagnostics. Reactive power compensation mechanism, balancing real-time and real and reactive power flow. Inductive load imbalance, motor and transformer causing lagging power factor due to reactive power demand. Capacitor supplies leading reactive power, concentrating the lagging demand from inductive load. Real-time adjustment, APFC dynamically adjusts capacitor engagement based on real-time load changes, optimize the power flow. Effective compensation minimizes transmission losses and voltage drops. Energy efficiency and cost saving, reduces energy losses, minimizes reactive current, lowering I square R losses across distribution system. Lower demand charges, improved power factor, reduces maximum kVA demand, thus cutting demand-based billing. Penalty avoidance, utilizes low power factor. APFC helps maintain compliance and avoid fines. Operational cost reduction, improve system efficiency, leads to lower electricity consumption and bill. Reduce penalty charge, enhanced lifespan of electrical equipment, lower thermal stress, voltage stabilization, extended maintenance cycle, improved equipment reliability. Stabilization of voltage level. Reactive power compensation helps balance the voltage drop caused by inductive load in distribution lines. Improved voltage profile, maintain voltage close to nominal level across varying loads conditions. Load balancing support, reduces unbalance and in effect in three-phase system. System-wide stability, stabilized voltage reduces disruptions and extended grid reliability. Environment and sustainability impacts, lower system losses, reduced carbon emissions, sustainable grid operations, support green certification. Intelligence APFC system, IoT enabled remote monitoring, predictive maintenance, self-diagnostic, cloud integration. Harmonic and their effects on APFC. What are harmonics? Harmonics are voltage or current is caused by nonlinear load like VFDs or rectifiers. Effect on APFs. Harmonics can cause resonance with capacitor, overloading them and reducing lifespan. Return react inductive react. reactor has used in APFC panels to prevent resonance and mitigate harmonics. Monitor solution. Advanced APFC use harmonic filters and analyzers for safe compensation. Challenges and limitations of APFCs. Sensitive to harmonics, initial investment, maintenance requirement, under and over compensation. Summary of APFC working and benefits. Real-time sensing, microcontroller logics and capacitor switching optimization, power factor automatically enhance voltage stability, reduce energy losses and extend equipment life, reduces electrical bill and eliminates utility penalty, sustainable load contributes to greener grid operation and supports compliance with energy standard. Future trends in power factor management, AI-driven operation, smart grid integration, edge computing, cybersecurity control system. Thank you.